I'm going to talk through an example in class today. So I am getting the Khan data, K-H-A-N, if you want to follow along. For these data, I have some example code that illustrates some of what we've been talking about in class, and in particular, illustrates cross-validation. Do we need more time for the homework? Yes? Okay. I'm happy to move the due date back a few days. How about, what if we did, I guess, so I posted on eCampus that we're going to have a guest speaker Monday and Wednesday of next week. So I won't actually be here to answer questions, although I will have access to eCampus. So how about we tentatively say, let's turn the homework in by Wednesday night. Okay. In fact, I'll change that now before I forget. Okay. So homework due Wednesday night now. We are in the middle of the Introduction to Statistical Learning notes, and we're learning specifically about cross-validation as a technique for giving us a good estimate of the accuracy of a predictive model. We've talked about how there's more than one way to characterize the accuracy of a model, and not every way is as good as every other. And in particular, if we use training data to both build a model and evaluate the accuracy of the model, we run the risk of overfitting our training data. The alternatives that we've seen are, number one, to split the training data into a training and testing subsets. If you did that, you would use the training subset for building the model and tuning it, and you would use the held out test set only for evaluating the accuracy. The purpose in doing it that way is that what we really want as an accuracy estimate is an accuracy that would apply if you took the predictive model to the general population and didn't just make predictions with the toy training data that you have. So one option is to split the data into training and testing, in which case you hold out the testing data and you only use it to evaluate the accuracy. Another option that is used a lot in practice is this cross-validation idea. So let me pull up our notes real quick. In the CV boot chapter, the general algorithm we can call k-fold cross-validation, where we choose k. There's a 5-fold cross-validation, a 10-fold, and there's leave one out cross-validation, which is essentially n-fold. The idea, as we said last time, is iterative. If we're going to do k equal 5-fold cross-validation, for example, We take our training data and we randomly split it into 5 subgroups. So every individual goes to one and only one subgroup. Then in iteration 1, the first fifth is used as a test set, and the remaining 4/5 is used as the training set. You build the model, then you turn around and apply it to the held out fifth and record the accuracy. Then iterate again, and now we're going to repeat that, but the test set is the second fifth at this stage. The remaining 4/5 are the training, and you build the model, apply it to the test set, and store the accuracy. Keep doing that k times, and at the end of it, you have k accuracies. K accuracies. And then the overall accuracy that you will claim, if we did, say, 5-fold cross-validation, at the end of doing the algorithm, we will have 5 accuracy measures. Suppose we're doing linear regression. We're trying to predict a numeric response. And each of 5 times, we build the regression model, and we evaluate its accuracy using mean squared error on the held out 1/5, or 1 over k of the data. So suppose we're doing linear regression, just as a simple example. Y is numeric, and I'm going to do 5-fold cross-validation. So I split the data into 5 groups, and I iterate through using each fifth one at a time as the test data. Within each iteration, we fit a linear regression model, and then we apply it to the held out test set, and we can record the mean squared error. I would then have 5 mean squared errors. I don't want 5 mean squared errors, though. I want to be able to say, for this particular predictive model, the estimated mean squared error is a single number. So what we do to combine those 5 MSEs into a single MSE is basically average them. The specifics here is that we do a weighted average. If there's n sub k training individuals, or let's say test individuals in the kth cross-validation fold, then this is the weighted average that we will use. If, for example, we do 5-fold cross-validation and each of the 5 sub-groups that we put together all have the same number of individuals in them, like suppose little n is equal to 100. Our training sample size is 100. If we did 5-fold cross-validation, we could distribute the 100 individuals into 5 equally sized subgroups of 20. Then after doing cross-validation, I would have 5 mean squared errors, and the way I would combine them into a single mean squared error is to just average them up. If it's 20, the same number in every training set, 20, then doing this, the sum of 20 divided by 100 times MSEK, that's just the sum of the MSEK divided by 5. So the big picture is you use cross-validation to iteratively split into train and test, and within each iteration, you fit to the training and evaluate with the testing, and store the resulting accuracy. After doing your iterations, the final cross-validation based accuracy is roughly the average of the k ones. If you can split your data into k groups of equal size, then it is exactly just the simple average of the k MSEs. Otherwise, if your training sample size does not divide evenly into k, you're going to have some of these subgroups that are bigger than others. And the general result is that your overall cross-validation based accuracy is a weighted average of the iteration-specific ones. So let me write this down on our whiteboard. If we have y as numeric, and we have, let's say, a single predictor variable that we'll say is also numeric, then we can fit, we can have in mind a model, a linear regression model that says the response is linearly related to the predictor plus or minus some random error. So on average, there's a linear relationship between x and y. Suppose we have training data in individuals. So I have y and I have x. In this illustration, we just have a single predictor variable. In past lectures, I've said we have y, which is an n vector, and we have x, which is an n by p matrix. So if we had p predictor variables, we would have an n by p matrix. But for illustration here, I'm just going to say, suppose we just have one predictor variable. So both y and x are n vectors. For, let's say, k equal 5-fold cross-validation, we split y and x into 5 groups. So let's say c little k is the collection of y's and x's such that I is included in fold k. So all I mean by that is C sub k is the collection of y and x pairs for the kth subgroup. Cross-validation is all about take all your n training individuals and split them into k mutually exclusive groups. For notation purposes, let's just say CK is all the response predictor variable pairs in fold k. So cross-validation would go like a for loop for k in 1 to capital K. And we would fit the model using everybody but K, everybody but the training individuals that were put into subset K. And we would evaluate the model using the 1 over K that is the current test set. And we would store the MSE kth one is the mean squared error that we would get by applying the currently fit model to the current testing data. This is a loop over k iterations. If k is 5, we're going to have 5 mean squared errors. At the end of this loop, we have capital K mean squared errors. And my overall mean squared error is then the, I'll cheat a little bit and just say it's the average. If I have 5 mean squared errors, 1 each for each CV fold, then my claimed overall CV-based MSE is the average of those 5. And that number, that accuracy, is in most important ways comparable to the accuracy you would get if you had just done a straight train test split. So with these data, with this application, I want to regress y on x, simple linear regression problem. And I have n training observations to do this with. One option would be, let's take, say, 2/3 of my n observations and use them as training data and set aside the remaining 1/3 as only to be used for testing. In which case, the for loop and the cross-validation stuff is not necessary, because we could just fit the model to the 2/3 training data and turn around and apply it to the held out 1/3 test data. The accuracy that we got on that 1/3 held out is a valid estimate of the generalizable accuracy, what we want. This cross-validation is a trick to get a number that's comparable to that one I just described. It's in some ways optimal to split the data into training and testing and just use that testing data for evaluating accuracy. But cross-validation uses an iterative trick to try to approximate that. At the end of the routine, regardless of which option we use, we're going to have an overall accuracy for the model we're considering. Cross-validation, we have to average over the CV folds to get this. So let me show you an example. I think it will help to see this in action. So over in R, we will look at the con data. So I downloaded con.csv and conscript.r. A little bit of background on these data. Let me load them in first and then comment on them. I'm going to run through line 40. This reads in the data and does some prettying up. Our X matrix, N by P, is 2308 by 83. There's more in this script than we need. I'll show you where the most relevant stuff is. So I'm actually interested in characterizing these data as 83 by 2308 instead of 2308 by 83. Has to do with the type of data these are, how they're organized. But these data, we have 2,308 variables, and we have 83 individuals. These are genomics data, which means that for each of the 83 individuals, each individual is a human being in this case, for each one of them, we have 2,308 numbers. Each number quantifies the activity level of a particular, let's say, gene. So for each of these 83 individuals, we have a snapshot of the activity level of 2,300 genes. We also have a response variable. So that data that I just showed you, the 80 by 2,300, is like the capital X matrix of features or predictor variables. In addition to those, if we're going to do predictive modeling, there needs to be some response variable. And I think the response is in the object called ID. So I created an object called ID. It's the same length as the number of individuals. If I table ID, it's a categorical variable. And if I table it, it will give me the frequencies of each possible value of ID. If you read the caption for this data set, the context is that each individual, each of these 83 people, have a tumor of a certain type. There's 4 types of tumors. The application is, let's take genetic information, a genetic sample from people, and let's see if we can predict which of the 4 tumor types they have. For example, if you have prostate cancer, as a middle-aged man, say, there's different flavors of prostate cancer. Breast cancer has different types of tumors. So do you have this type A that's super aggressive, or do you have this type B that's easily managed with diet, or what? Let's use a genetic snapshot to make predictions about which of these 4 tumor types does an individual have. That's what we're trying to do. Let me kind of talk through beginning at line 178 in the script. Beginning at line 178 is all about predictive modeling with these data. Remember that if we're doing predictive modeling, supervised learning in the language of the textbook, we have to distinguish between, is our response variable that we're trying to predict, is it numeric or is it categorical? It can be either one. Back here, we were playing pretend that the response was numeric. With numeric response, a natural measure of accuracy is mean squared error. But if y is categorical, as it is here, it only takes values 1, 2, 3, 4, and those don't have numeric meaning. They're just placeholders for different tumor types. If the response is numeric, at least the authors of the Introduction to Statistical Learning book will call the problem regression. If the response is categorical, they call it classification. Both are predictive modeling. We have training data, y comma x, and we want to build a model y equals some function of x. But if y is numeric, we're doing what's called regression. If y is categorical, we're doing what's called classification. So everything below line 178 is classification with these data. One way we could proceed is the gold standard way, which is to take your 80-something individuals and split them once into training and testing sets. So line 182 is doing that, line 182 and following. I'm going to set aside 2/3 of the samples for training. The remaining 1/3 will be only used for testing. When it comes to doing this, taking your 80-something individuals and divvying them up into training and testing, the best practice is to do that randomly. As in, don't just take the first 2/3 in your training set as training and the last 1/3 as testing. Because it may be that there's some systematic differences across the rows. Maybe the first 10 were done in a batch, the second 10 were done in a batch, and so on. So best practice is to randomly pick, and that's what I do here. We don't have to go through this in detail, but this is a little bit of code to randomly pick 2/3 of the data. And let me just run this and show you what we end up with. I created a data frame called y_df, like y data frame. This is 83 by 2309, one row per individual, and then I have separate columns for each of my 2308 predictor variables, and I have a column for the response. Called it group. Let's look at the first 5 rows, the first 5 columns. Each row is a person in my training data set. The x1, x2, ... goes all the way out to 2309. Those are all the features, or the genes, the predictor variables. And then my response, I put in the first column. Call it group. But we want to use the x's to predict group. After running this code, I have the data in a data frame, and I split that into 2 data frames. So there's a data frame for training and one for testing. Show you those over here. Y_train is 54 randomly selected from the 83, and Y_test is everybody else. Okay. I will skip this. Actually, let me comment on this real quick. Naive Bayes. In your homework, you have LDA and QDA as what you're asked to do. And it turns out that LDA, QDA, and something called naive Bayes are all very closely related to each other. So let me explain that. In the context of Y, a categorical response, and X, a P vector of predictive features, predictive variables. One way to proceed in a classification problem is to make some distributional assumptions. In each of these, LDA, QDA, naive Bayes, we make an assumption that the vector x, if you tell me which class it came from, is a multivariate normal with some mean vector that depends on the class and potentially a covariance matrix that depends on the class. In our case, we have 4 classes, 4 tumor types. So what we're saying is that the vector of gene intensities, the X1 through X2308, if you're in class 1, tumor type 1, that has a multivariate normal distribution with a mean and a covariance matrix that's specific to class 1. If you're in class 2, you're again multivariate normal, but you're allowed to have a different mean and a different covariance matrix. This expression specifies a likelihood. A likelihood is a consequence of a probability distribution that you assume for the x variable. If we said the x's were multivariate normal like we do here, we're specifying a likelihood. If we also specify what we'll call prior probabilities, these are without considering the input variables or the features. Independent of those, if you just randomly picked an individual from the population of interest, what would you say is the probability they have tumor type 1? And what's the probability you would choose prior to seeing data that the tumor type is 2, and so on? Prior distributions or prior probabilities are probabilities that you postulate that are independent, not with respect to any data. Prior to seeing the data, I'm going to say, maybe I would say, well, I think all 4 tumor classes are equally likely. In which case I could say my prior probabilities are 1 over 4, comma, 1 over 4, 1 over 4, 1 over 4. Without seeing data, that's my best guess at how likely the different tumor types are. With this setup, a likelihood and a prior, we can apply Bayes' theorem to say that the posterior probability, that's the probability that the class is a particular class given the data, is proportional to the likelihood times the prior. Bayes' theorem is just a trick, probability trick, for switching the ordering of conditionals. A likelihood is basically a probability of seeing the data we saw for a given choice of parameters, or in this case, class membership. For tumor class Y, the distribution of the input variable is multivariate normal. That's a likelihood specification. Combine a likelihood with a priors, and you have Bayes' result. Likelihood times prior will be proportional to the switched ordering of conditionals. If the likelihood is the probability of seeing your data if it's tumor class Y, the posterior is the probability that it's tumor class Y given that you observed this data. That's a very sensible quantity to estimate for classification. Makes a lot of sense. If we can estimate, given your data, the probability you're tumor class 2 is makes sense to use that as the basis of our classification. Okay, if that number is bigger than, if that number is sufficiently big, I'll predict that you're class 2. I mentioned in a previous lecture that in terms of operating characteristics, like how many errors you make, the best classifier you can get is the Bayes classifier, this posterior probability, and then predict class Y if the posterior probability of class Y is sufficiently big. That's an optimal classifier called the Bayes classifier. LDA, QDA, and this naive Bayes all approximate this. So they say, let's assume multivariate normal. Let's come up with some prior probabilities. Then let's apply Bayes' rule to get posterior probabilities and make our predictions based on that. So QDA is based on the above model as stated. LDA assumes that the covariance matrix doesn't change across classes. The likelihood statement up above allows for each class to have its own mean and its own covariance matrix. That model is the quadratic discriminant analysis, or QDA model. You can simplify that model, make it so that there's fewer parameters that you have to estimate, if you assume that all the covariances are the same. That's linear discriminant analysis, LDA. And then naive Bayes says that there's a single covariance matrix and it's diagonal. So what that says is the features are independent of each other. That's naive in the sense that most features are not independent of each other. Genes, for example, we know that genes operate in a correlated way some of the time at least. Some genes are correlated with other genes. So that naive Bayes idea is a very, very simple model. Makes very strong simplifying assumptions. But I think this is a good slide to stare at a little bit, just to get a real clear understanding of this classification task. If you understand this, then all the other classification techniques, you have a foundation to put them in. They're all doing something like this. It just turns out that LDA, QDA, naive Bayes can be formulated really cleanly in terms of an application of Bayes' theorem. Back in the slide, or in the script, I have a section for doing the naive Bayes prediction algorithm. Turns out there's a built-in function for that. We don't need, well, I'll go ahead and let's see if I have this package. Install. I'm going to try to install the package that contains the naive Bayes function. It's called E1071. All right, so I libraried that in. And here is some general syntax that for many predictive model types, you'll make very small changes to. For naive Bayes, in order to fit the naive Bayes model, we can use the naive Bayes function. And let's look at the syntax here. This is saying fit a model. R likes to specify model relationships with like response tilde predictor. So the first argument is a formula or model type statement. Group is my response. Remember, there's a column in our data frame called group. So group is my response, and I want to model it in terms of, if I say dot in a formula statement, that means use all the predictor variables that we have. So we have this y train df. In the number of training individuals currently is 54. I have one column for the class membership, and then I have 2,308 columns containing predictor variables. When I say this, fit the naive Bayes model with group as the response, tilde dot, that's telling R to use all 2,308 variables as a feature or a predictor variable. So it's saying that the distribution of my training data given a particular class is a 2,308 dimensional multivariate normal. And there's a separate mean vector for each of the four classes. So I say fit the model with group as the response using all the predictors. The other argument I can specify is to provide a data frame that contains the data I want to use for building the model. Since at this point we've split the data into training and testing, the y-train df contains 2/3 of the training individuals, and I want to build my model at this point using just the training individuals. So I say data equal y-train df. You build your predictive model with the training data. And the test data are then used only to evaluate the accuracy of the model. Many of the predictive models that you'll meet in the upcoming weeks can be modeled in this type of with this type of language, where you say my fitted object gets naive Bayes or LDA or QDA. You can interchange lots of different predictive model types with the naive Bayes here. But the fit underscore whatever is your fitted object. And then the next step is to use that fitted object to make predictions. And there is a generic predict function in R. Remember that in R, a given function may do different things depending on what you pass it as an argument. Predict, for example, does lots of different things in R. If you want to do prediction on a naive Bayes object, and you want to learn about how to use that function, here's a trick. So if I just say $predict, I get the generic help file for predict. The function invokes particular methods that depend on the class of the first argument. That just means it does different things depending on the type of object you give it. So this is not actually all that useful for our script right now. What I would rather see is the help file that is specific to naive Bayes. With a function like predict that has a general representation and specific meaning for different object classes, you can find the help file by saying !, generic function name, dot, the name of the class that you want to apply it to. In our case, the name of our class, whenever I fit this model, if I ask for class of fit in B, I get naive Bayes. And there is a version of predict that is specific to naive Bayes. So here's where you want to go if you want to figure out the details of how to do predict with a naive Bayes. It shows you how to use the naive Bayes function itself. And then here is the version of predict for an object of class naive Bayes. So back here, let me just illustrate this and I'll let you go. I have fit the model using my 2/3 training data, and now I'm going to make predictions. Use the fitted model, and now let's plug in the held out test data. The new data I want to make predictions for are the test data. These were not used at all in the previous step. They haven't been touched yet. So if I say this command, what I have is a separate prediction for every test individual. When we split into training and testing, we were left with 29 test individuals. When I used the predict function, it gave me back 25 categorical values. For the first individual that was in the test set, I predicted class 2. And for the second, I predicted class 2, and then 2, and 2, and then I predicted 4, and so on. How well did we do? We could make what we called last time a confusion matrix. Cross-tabulate the predictions with the truth. You can do that with the table function. That's the confusion matrix for the naive Bayes predictive model with these data. The diagonal represents correct predictions. There were 4 cases where the truth was class 1 and we predicted correctly class 1. There was 1 case where the truth was class 2 and we incorrectly predicted class 1, and so on. Here is the overall accuracy. If you tallied up how many off-diagonal non-zero entries are there and divide by the total number of predictions, that would tell you overall the proportion of correct predictions. So 86% of our predictions were correct. All right, I didn't get as far as I wanted to, but I will point you to the con script for some more examples. And specifically, there is k-fold cross-validation illustrated. Doing this is more complicated than what I've asked you to do in the homework. Leave one out cross-validation is very simple to code up. You just need a for loop, and within the for loop, you set aside a single individual for testing, and you use the remaining n-1 for training. Yeah, but so I've moved the homework back till Wednesday, so you do have some extra time, but I recommend you work on it over the weekend, and let me know or post to the discussion board if you have questions. Okay? All right. See you. Remember that you'll have a guest speaker Monday and Wednesday. So Dr. Gainanova, who's an expert in multivariate statistics in our department, she'll cover for me Monday and Wednesday while I'm gone on a business trip. So watch for her. She'll continue talking from the Introduction to Statistical Learning stuff. And then I will see you in class on Friday. Okay. Have a good weekend.